The periodic table is a tabular display of the chemical elements, which are arranged by atomic number, electron configuration, and recurring chemical properties. The 7 rows of the table, called periods, generally have metals on the left and nonmetals on the right. The columns, called groups, contain elements with similar chemical behaviors. 6 groups have accepted names as well as assigned numbers. For example, group 17 elements are the halogens, and group 18 are the noble gases. Also displayed are 4 simple rectangular areas, or blocks, associated with the filling of different atomic orbitals. An atomic orbital being the space or region around the nucleus where the electrons are calculated to be present. Different shapes of orbitals are drawn depending on the possibility of finding electrons around the nucleus. So we have S, P, D, and F. Atoms are made up of a positively charged nucleus surrounded by a cloud of negatively charged electrons. Nuclei are very dense and extremely small. They contain more than 99.9% of the mass of an atom and are 10,000 times smaller than an atom. The nucleus is a collection of particles called protons, which are positively charged, and neutrons, which are electrically neutral. Protons and neutrons are in turn made up of particles called quarks. The chemical element of an atom is determined by the number of protons, or its atomic number, Z, of the nucleus. The element oxygen, for example, has an atomic number of Z equals 8, while carbon has an atomic number of Z equals 6. So that means that oxygen has 8 protons and carbon has 6 protons. The atomic mass of the nucleus is given by A equals Z plus N, where N is the number of neutrons in the nucleus. So that means when we want to find how many neutrons would be in the nucleus, we would subtract the atomic mass by the number of protons, and it would give us the number of neutrons. You can see this calculation is done here. The Schrödinger equation dictates the energy order of the orbitals, but they can also be readily determined just by looking at the periodic table. An Aufbau diagram seen here uses arrows to represent electrons. When there are 2 electrons in an orbital, the electrons are called an electron pair. Electron pairs are shown with arrows pointing in opposite directions. An arrow pointing up denotes an electron spinning one way, and an arrow pointing downwards denotes an electron spinning the other way. If the orbital only has 1 electron, this electron is called an unpaired electron. Electrons are placed into the atomic orbitals, filling from the bottom to the top, kind of like water in a jug. So from the lowest energy to the highest, or from the most stable to the least stable. So, for instance, we would fill 1s before 2s. We would also fill 4s before 3d. In general, the energy order of the orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. You can watch as I fill the orbitals for germanium using these rules, being sure to fill 4s before 3d. Hund's rule of maximum multiplicity states that if orbitals of equal energy, which we call degenerate orbitals, are being filled, the electrons are placed into each orbital in the degenerate set before they are spin paired with another electron in the same orbital. So for example, if we look at the p orbital, it has 3 degenerate orbitals. Again, they are called degenerate because they all have the same energy level. Only 1 electron will be placed into each orbital before they begin to be paired. You can see I follow this rule as I fill up the orbitals for germanium. As you can see, the germanium atom is now completed. If we look at our diagram, the last 2 electrons in the 4p orbital are going to be left unpaired, following Hund's rule of maximum multiplicity. And here it is, our completed germanium atom.